what I'm going to do is quickly once again go over the implementation of the biquad filter in a folded architecture, right, at least some parts of it, so that we can once again just review some of the decisions that were taken, how the architecture and how the choices of scheduling instance that we make translate into the hardware implementation. Okay. So, to do that I am going to quickly just redraw the circuit that we started with. So, the numbers that I am writing up here are just identifying numbers for the different nodes. So, I will just call this node number 1, 2, 3 and 4. So, in other words, nodes 1 to 4 are adders, 5, 6, 7 and 8 are multipliers. Okay. For the multipliers themselves, I am showing only one input, the other input is a coefficient, and since that is constant I am not going to show that as a separate inputs, but of course all the 4 multipliers have different coefficients associated with them. Yeah, so the 4 multipliers have the labels that I am giving to them are 5, 6, 7 and 8, and the coefficients I am not indicating over here. We will just use some variables to indicate them when necessary. Okay. There is an input which I will just denote by in over here, and an output, that is out. You can call it x of n, y of n, it does not matter what exactly is the terminology used there. And the next thing that is required over here is that I need to specify the folding schedule, right, the time instance or the phases at which the different operations are executed. Now, I think the numbers that I had given the last time around in class, there was some confusion regarding those. So, please bear with me, the numbers that I am giving now are what I am going to use for the rest of the implementation. Okay. So, the time instance are basically, I am writing them down in red over here. This is at time 3, this is at time 1, 2 and 0. So, in other words, we can see that there are 4 additions scheduled at the time instance 0, 1, 2 and 3 corresponding to 4 phases of the clock. Okay. Similarly, the multiplications are, this one is 0, this is 1, this is 2 and this is 3. Okay. So, the red numbers in other words indicate phase of clock for executing that operation. So, what we have is n, the number of phases is equal to 4. The folding sets themselves are S1 for the adder corresponds to operation number 4, then operation number 2, then operation number 3 and operation number 1. This is for the adder, and S2 is equal to 5, 8, 6 and 7 for the multiplier. Okay. So, couple of things to again keep in mind over here. In this original diagram, this diagram that I have drawn over here, even though it is strictly not speaking a data flow graph, you need to be a little careful how you interpret it. The way that I have drawn it, it is not exactly a block diagram corresponding to a final architecture either, right, because an architecture would actually mean that physically I have this many adders, this many multipliers and so on, and what I am drawing over here is with 4 adders, 4 multipliers, whereas what I am saying is I am trying to get an implementation that has only one hardware adder and one hardware multiplier. So, this diagram is sort of closer to a data flow graph than a hardware block diagram in that sense. What it is showing is only the connections between the different nodes, the dependencies, and also how many delay elements, sample delays are present on the edges that link different nodes. Okay. Because of that, you need to sort of interpret this a little bit carefully. What I mean by that is, so for example, this line that I have drawn in magenta over here corresponds to one edge in the data flow graph, right. This is the edge from node 1 to node 6 with the number of delay elements on it is equal to 1. This W is the number of sample delays. Okay. Similarly, I have another edge that goes over here from, this is an edge from node 1 to node 8, and it has W, the number of delay elements, equal to 2, right. Both of these delay elements, in other words, correspond to this magenta edge that I have drawn over here. Okay. So, I have drawn it in this fashion so that it is compact and easy to sort of visualize what the structure looks like, but in order to actually interpret what are all the different edges that need to have implementations when you fold the architecture, you need to actually take what are the operational nodes, what are the adders, what are the additions that need to be done, what are the multiplications that need to be done, and find out the connections between them directly. How many sample delays are on those edges between them. Now, with this structure in mind, we then went forward and said I can now compute something called a DF value, right. And the DF value was essentially, it's something like what are the extra delays or the extra number of registers that are required in order to get the data correspondingly to the right input at the right time instant, right. To understand that a little bit better, let us take a couple of examples. I will look at the edge from 1 to 2, okay. This edge from 1 to 2 has W equal to 1, okay, alright. So, let us work through that. This has W equal to 1. The schedule time of operation number 1 is at time 3 and operation number 2 is at time 1, okay. So, this was scheduled at time 3, this was scheduled at time 1. So, the DF therefore, the time when 2 was scheduled, or in other words, let me just write that out clearly, it is the time of operation number 2 minus the ending time of operation number 1, T1 plus PA, the pipeline latency of the adder, this plus N into the W. So, in other words, it is equal to minus of 1 minus 3 plus 1 plus 4, okay, or 4 minus 3 equal to 1, okay. So, I wrote it out in this fashion so that it becomes clear how I arrived at it, right. This T2 is the time when 2 is scheduled, T1 is the time when 1 is scheduled, T1 plus PA is the time when 1 completes and therefore its output is ready. Therefore, T2 minus T1 plus PA would be the extra number of, would be basically, I mean, so T1 plus PA is the time when 1 has finished, T2 is the time when that product, that value is then consumed, okay. And if there are W delays, then T2 plus N into W is the time when it is consumed, okay. T1 plus PA plus N into W is the time when it is consumed, okay. So, another way of looking at this is T1 is scheduled at, or rather operation 1 is scheduled at time T1, completes at T1 plus PA. Operation 2 is scheduled at T2. W delays correspond to N into W clock cycles. In other words, if I want to use the value produced by operation 1, W samples later, then that will correspond to the execution of T2 at T2 plus n into W, right. The data that was produced at time T1 plus PA is going to be consumed at time T2 plus n into W. For that much intermediate time, I need to store that value, okay. That is the number of extra physical registers that I will need to allocate somewhere to save the data until it is ready to be consumed, which is what we have over here. The time of T2 was 1, this was 4 into 1 minus 3 plus 1. So, it finally becomes equal to 1, okay. Once, the reason why I am working through this is I want to make sure that all of you understand how this was arrived at, because finally what you will probably end up doing is just use a formula, right, because after all I can just simplify this formula and say that in general df from some node u to v is equal to time of v plus n into the number of delays between u to v minus Tu plus. So, in general you can compute the df value like this for any pair of nodes in the original graph. If we go back and look at this, I can pick any pair of nodes and write down the df value in this way and compute it, okay. So, let me just write that down for a couple of more edges just for clarity. So, for example, we will take, let's for example take node number 2 itself, find the other element that is leading into it, which is basically an edge from 4 to 2. So, df in other words from 4 to 2 will be equal to the execution time of the target 2 is time 1, the number of delays on the edge is 0. So, 1 plus 4 into 0 minus 0, which is the time when operation number 4 is scheduled, plus the latency of operation 4, which is an adder. So, df from 4 to 2 becomes equal to 0, okay. So, I am not going to work through the rest of this. What I would suggest that you do is, I have already uploaded the link to Professor Parhi's website, where one of the slides for chapter number 6 actually contains the details of the exact implementation for this biquad filter structure, right. So, what I am going to do is just pull that up over here, right, and over here what we can see is that the folding equations for every one of the 11 edges has been drawn, okay. So, let us just go back here and look at this. There are 11 edges if you work through it, basically corresponding to each of the different inputs that we have coming in over here, right. So, from 1 to 2, from 1 to 6, 1 to 5, 1 to 8, 1 to 7, etc. You work through it, total number of edges are as seen over here.